This is video 2 for the basic concepts of electricity, and what we're going to do with this one is we're going to start talking about circuits now. When we last left off, static electricity, it was discovered, is created when two objects rub together, and electrons will be transferred from one object to another. Electrons, it turns out, when we have different atoms, electrons have different degrees of freedom. So in metals, for example, room temperature heat energy is enough to cause the electrons to leave their atoms and move around. So we call these free electrons when it comes to metals. So these electrons are moving in between, going from atom to atom to atom. And these electrons are very, very free. Other materials, such as glass, however, are going to keep all of their electrons closely attached to their atom. So what that means then, if you were to take some silk or something and rub it against a piece of metal, the metal will not become, statically charged, because any electrons you take away from that metal, it can gather from the air around it. So you cannot charge a metal in that way. Or another way of looking at it, it's very, very hard to take the electrons away from that silk cloth. Now, when you take two insulators and rub them together, the electrons can be ripped. If you can rip the electrons off of one material and give it to the other, the electrons will become trapped on that material. So when we rub two materials together to make them statically charged, the two materials have to be non-metals. They have to be insulators. Now, the relative mobility of electrons within a material is known as its electric conductivity. So materials with high electron mobility are called conductors, while materials with low electron mobility are called insulators. So here's a graphic here. On this side we have our insulators, so rubber is a very good insulator. And on this side we have conductors, and silver is a very good conductor. Silver is a better conductor than copper. However, we don't use silver to wire our houses because copper is cheaper. It should be noted, though, that glass and dry air, especially at high temperatures, these will become conductors. So the electron mobility is also dependent on how high the temperature is. Now, while the normal motion of free electrons in a conductor is random, those electrons, they go anywhere and everywhere, we can influence the electrons to move in a certain direction. So this uniform motion is what we call electricity. So in order to do this, we need to provide a path for those electrons to follow. Usually we use wires, which are copper metal surrounded by a rubber casing. So we've got a conductor surrounded by an insulator. The path, however, cannot have any breaks. If we want these electrons to move continuously, we need to have a circuit. So a circuit is something that finishes where it starts. So for example, if I have a wire, that would be a circuit. So the electrons can flow around in the circuit. If there's a break, the electrons cannot jump over that gap. And the reason why is because air is a very good insulator. The air would prevent those electrons from jumping across that gap. So all circuits cannot have any breaks in them in order for the electricity to flow through them. So we need to talk now about voltage and current. Electrons, as I said before, need a continuous path to follow, which we call a circuit. But how do we get the electrons to follow that path? There needs to be some kind of influencing force to initiate that flow. We need to have some sort of force to push those electrons through the wire. So let's say we have an object that's positively charged and a second object that's negatively charged. As we discussed before, there's going to be a force of attraction between these two. So if we were to attach a wire between those two objects, the electrons would follow this wire and join the positive part on the other part. Now, the electrons can move, but the protons can't because protons are locked inside of a nucleus. So the protons are not free to move. The electrons are. But this force would provide the motivation to push those electrons through the wire. So, as I say here in this statement, the imbalance of electrons between the objects creates a force. By providing a path to follow, the electrons will move in the direction that we want them to move in. Now, the act of charging an object initially took energy. If I rub two materials together, I'm doing work. It takes energy for me to rub those two objects together. We can think of this like a pump. So let's say we have some water in a reservoir, and we have a pump that pumps the water into a tank above. Moving the water from the lower area to the high area, well, it takes energy. And what we're doing by pumping this is we're going to increase the water's energy. So by doing that, by the act of moving the water, we are storing energy in the water. And then if we were to punch a hole in the bottom of this, we would be able to recover that energy that we stored in it. You know, the potential energy in here would turn into kinetic energy of the water falling down. Now we could do this a different way. We can turn this into a circuit if we wanted to, where we have our water in this reservoir. We pump the water up, and then we provide a return line for the water to come back down to the reservoir. This water now follows a circuit. And something to notice is that even more energy can be stored in the water if the tower is taller. If we positioned it even higher than the reservoir, we can get even more energy. But it would take more energy to operate the pump to pump the water into an even higher tank. Electrons, it turns out, are not much different. By rubbing the materials together, we are pumping the electrons from one location to another. This stores energy in the electrons, and we call stored energy potential energy. So the potential energy stored in the form of a charge imbalance is capable of moving the electrons through a conductor. We express this as the term called voltage. So what voltage is the energy per unit charge and the higher the voltage, the more potential energy each charge has. how electrons flow from high voltage to low voltage. So if I have something up here that has, let's say, positive 10 volts, if I have something here that has, let's say, positive 3 volts, if I were to connect this with a wire, the electrons would flow from the 10 volt to the 3 volt. So electrons want to flow to where there's less voltage. Now, defined in the context of static electricity, voltage is a measurement of the work required to move a unit charge from one place to another. Defined in the context of electrical power sources such as batteries or generators, voltage is the amount of potential energy available per unit charge, so work to be done to move the electrons through a conductor. Now, because voltage is expressed in terms of potential energy, we always refer it between two different points. So for example, let's say we have a battery. The symbol for battery is a series of long and short lines where the long line is the positive terminal, the short line is the negative terminal, and we get a voltage here and a voltage here. And what we do is we look at the change in voltage. In terms of water, if we were to have, let's say, our reservoir tank here, and we're going to pump water up here. If I were to have like two spigots, it'd be like the difference between the height of those two spigots. Now, voltage can be generated by other means than rubbing certain materials together. Chemical reactions, such as batteries, can have a voltage. Radiant energy, such as solar panels, can have voltage, and the influence of magnetism on wires, such as electrical generators. Those can also have voltage as well. All right, well, that concludes video 2.